Welcome to the lecture number 14 of Irrigation and Drainage lecture series. So, in this lecture we are going to learn some of the irrigation water measuring devices both in open channels as well as in pipes. Okay. So, here continuing to the previous lecture, that is the lecture number 13. So, there is a Deflection meter. This is an open channel measuring device. So, this is named after J.S. Deflection of Australia. So, basically it consists of a drum which is mounted on an axle with 8 V shaped vanes. If you see these are all V shaped vanes. So, this is a drum which is rotated on an axle. This is an axle and which consists of V shaped vanes fixed outside the surface of the drum. So, in this the main principle is the number of rotations which is caused by the flow of water is being accounted or on the and that's been calibrated. So, the number of rotations will give the discharge. Okay. So, it basically sits laterally across the channel and is turned by water flow, because water itself causes the rotational rotation of the drum, and a short concrete outlet formed to provide only minimum clearance. So, here if you see here, so this is the concrete. So, that will create a minimum clearance. Okay. So, minimum clearance between the V shaped vanes and this one and the concrete, so that there will not be any water loss. Okay. Water loss which is not accounted here. So, basically the meter provides a direct discharge measurement corresponding to the number of revolutions by the counter. So, here there is a video, hopefully. So, this okay, anyway it is not working anymore. So, as I said, so Deflection meter rotates based on the flow, and the number of rotations will be accounted. Okay. So, the number of rotations will correspond to the discharge of the particular open channel flow. Okay. So, here the trajectory meter, this is a simple principle, a works principle on the trajectory or projectile, you might be knowing. So, here if you see, so let us say this is a block and you have thrown an object. So, the object will take a parabolic shape. So, that is well known, and from this point the vertical distance is estimated by y is equal to half g t square, and the horizontal distance is estimated by x is equal to v naught into t. So, in this the horizontal distance and the vertical distance, I mean the t from both equations will be substituted. So, then first of all here let us say v naught is equal to x by t, right. So, then get here 2 y by g and t is equal to where t is equal to square root of 2 y by g. So, substitute this t in here and then you will be able to get this equation v naught, and so q is equal to c into a into v, then substitute whole equation here like pi by d square, this will be the area of cross section, and then this is v, and then c is the correction factor. So, the trajectory meter works on the principle of projectile, and here mostly so make sure that the pipe is full, and this is the diameter. So, from the diameter you get the area of cross section, and this is the point of release, this is the point of release, and from here you are going to find out the x and y, right. and so if you have a scale, you can find out what is x and what is y. So then you can substitute x and y and find out V naught here. Okay. So the next open channel flow meter is orifice meter. So the next is the orifice meter. So this is basically works on the principle of orifice. So for example, if you see here, this is the tank, right. So the tank has a hole here, right. So the circular hole, it could be a circular or rectangular hole. So this is the head, and if you see here, there are the two correction factors we have to find out. What is the discharge correction factor, then other one is velocity correction factor. Okay. So this is supposed to be 0.5 and this is also 0.5 or the square root. Okay. This is the square root. Okay. So from here, so knowing the head h, okay, so you can find out CD, CV and A area of cross section. If it is a circular hole, you will have circular pi by 4 d square, and then so if this is a submerged case, suppose this is H1 submerged H2. So the difference is delta H. So you can substitute in place of H delta H, and still you can find out the discharge from the submerged orifice. So CD values generally varies from 0.6 to 0.8, and CV, the correction factor, mostly it is taken as 1 in case of open channel flows. So the next open channel flow meter, before going to that, there is an example. If you see this example, so determine the discharge of a 4-inch diameter end cap orifice on a 6-inch diameter pipe, okay, if C is equal to 0.7 and head of the orifice is 12-inch. Okay, so head is given, that is the 12-inch H, and G and C is given 0.7, and here the discharge of 4-inch diameter end cap orifice in 6-inch diameter pipeline. So the difference will be 2-inch. So orifice diameter is 2-inch. So the 2-inch you convert into centimeters. Okay, so you get area 81.08 centimeter square, and Q is equal to, this is the equation. So this is square root, of course. So 0.7 into 81.08, and then substitute the values, and finally you get Q is equal to 0.02 meter cube per second. Okay. So the next is the Parshall flume. Okay. So the Parshall flume, so basically what happens, so the whole water channel is being converged and then channeled and then diverged. So these three actions basically taken place in Parshall flume. So it can measure up to 1500, sorry, it can measure up to 1500 million gallon per day. So that is around 5.7 million meter cube per day. Okay, so as I said, so this is a convergence section. So the flow basically takes place from this end to this end. Okay. So initially the flow here will be converged. Okay. So then these are the measuring scales, scale 1 and scale 2, and this is the diverging section, and in between there is, this is called a throat section. Okay. So basically it consists of 3 parts: the converging section, throat section, diverging section. So the starting is, so the throat section basically has the scale. Okay. So these are the, I mean, dismantled view if you see. So initially it made up of metal. So then this is the installation, if you install this in the field, and then the next is, so if you see the Parshall flume, So, it is based on, I mean, denoted based on the throat width. So, if you have throat width 1 inch, so the flume is represented based on the throat width. So, 1 inch flume means 1 inch throat width. So, it measures around 0.28 LPS. With 50 foot flume, so that can measure up to 84,950.5 liter per second. So, the dimensions are standardized for each flume. So, if you see here, so this will give the dimensions of different sizes of flume. So, here W is the throat width. So, this is the flume size. So, each size, so these are the other labels presented here. So, A 2/3 A, B, C, D, E, F. So, you can check here. So, the lengths or the dimensions are decided based on this particular table. So, here it relates H A or H A and H B if it is submerged to the discharge. So, H A, this is the head at head end, okay, whereas H B is the head at downstream end. Okay. So, discharge rate equation or consult appropriate chart. So, there you can have some equations to relate the discharge and H A, or there are some charts available to get the discharge corresponding to H A and H B. Okay. So, again continuing to the Parshall flume. So, as I mentioned, there are two kind of flows, what is the free flow and submerged flow. In the free flow case, it requires only one head H A. So, here in the free flow case, so these are all the water level indicators. So, this is one water level indicator or stilling well you can say, okay, H B, and there is H C also, which is at the downstream side. Okay. So, basically we look at H A and H B. So, so H A, the formula Q is equal to C H A power n, C and n are the constants, and so if it is free flow, knowing the H A, the water level at the head end multiplied by C and n will give the Q. So, C and n, the exponents we can get it from the table. So, submerged flow, so the two head readings H B and H A. So, basically 1 to 3 inch flumes we allow 50% submergence. Okay. So, that is submergence is measured with H B by H A. So, submergence is equal to H B by H A. So, for 1 to 3 inch flumes we allow 50% submergence. So, then you can use this equation if it is 50% submergence, and if it is 6 to 9 inch flumes we are going to allow 60% submergence, like 1 to 8 feet flumes we allow 70% submergence, more than 80 feet flumes 80% submergence. If it is more after 90% submergence, the flume does not work anyway. Okay. So, the next so those are the flow measurement devices in open channels. Now, the pipe flow measuring devices. So, these pipe flow measuring devices like Venturi meter. So, this Venturi meter, this is also known as a common differential head meter. So, if you see here, this is the flow which is going in and going out. So, the Venturi meter has I mean, if you take a cross section of flume or cutthroat flume you can say. So, that means in that there is no throat section. If you see here, there is no throat section, but this is almost similar to a flume. Okay. So, this is enclosed view, this is cross section view of the pipe. Okay. So, here the diameter 1, this is a converging section and the diverging section D3, and there is a cut throat. So, this is the D2. So, this is the manometer and this is the manometer if you see. So, that difference in water levels will give the head. So, using that head, this is h. So, this is the head and the diameter d 1 and d 2, and A is the area of cross section, okay, area of cross section A 1. So, that is here, this is the area of cross section, and C D this correction factor. So, Q is equal to C D into A 1 into square root of 2 Z H divided by d 1 by d 2 whole square minus 1. So, this equation will be used for measuring flow in Venturi meter. Okay, generally for Venturi meter C D is equal to 0.97, and we are going to see the similar kind of equations for next few pipe flow measuring devices. Okay. So, and then the next pipe flow measuring device is nozzle meter. So, nozzle meter, it is a simplified form of Venturi meter. If you see, so here the basic difference is there is no converging or diverging sections. Okay. This is a complete a single piece of pipe which has d 1 and d 2 which has a single pipe, but at the center there is a nozzle. Okay, that is a nozzle which has a diameter d 2. So, so the difference here, the pressure difference, so H 1 and H 2, so that is the pressure difference H. So, this is basically this H is this is a gradual downstream expansion Venturi is eliminated. So, higher head loss than Venturi. If you see the head loss, so this will be more than the Venturi, you can see. So, not used extensively in irrigation water measurement, and the discharge equation is same as Venturi meter. You can use the same equation as Venturi meter for nozzle meter. Yeah. Okay, so the next is orifice meter. So, here this is another differential pressure meter. So, we have a Venturi meter, a nozzle meter, and orifice meter. So, these three are like pressure differential pressure meters. So, differential pressure here, this is a pressure 1 and pressure 2. So, the difference on pressure will be plugged into the equation, and then we estimate the flow discharge. Okay. So, the often used to measure well discharge. So, this one, and also measure the chemical injection. In this case, since it is a orifice, so it can also be used as a chemical injection, and the required long straight pipe lengths and full pipe flow is required. Of course, in all these differential pressure meters we need full pipe flow and a limited discharge ratio, and discharge equation is identical to Venturi meter, whereas C D is equal to 0.66. In Venturi meter the C D is equal to 0.9, right. So, that is the only difference here. And then the next is elbow meter. So, this is another meter. This is works on the principle that when liquid travels in circular path, centrifugal force is exerted along the outer edge. Suppose, so the flow is taking place here in a circular path. So, the centrifugal force which is going to act on the stream. Okay. So, that is the main the principle, that means this band basically is throwing the fluid out. Okay. So, here the P out and P in, so the differential pressure, so which is the pressure difference between inside and outside in elbow is being calibrated. Okay. So, knowing the discharge and creating the different pressure differences, we will give the delta P and Q. So, knowing the pressure difference, you will get the discharge. Okay. And the next is the propeller meters. So, the propeller meters simply will have a propeller inside, propeller in the sense. So, the axle will consist of different blades, axle blades. So, the multiple blades that rotates in horizontal axis basically operates on Q is equal to A into V principle. So, that means the number of rotations. So, that will give the velocity and multiplied by the area of cross section. So, that will give the Q. So, usually have a totalizer plus instantaneous discharge display. So, here, so this can be the instant discharge as well as the totalizer. Totalizer in the sense for a particular time period, the particular time period you can get individual discharges as well as the total discharge for 10 minutes or 15 minutes, the whole 1 hour, something like that. And the accuracy can be 2 to 5% of actual flow, must be installed in manufacturer specifications for accurate measurement. So, manufacturers are going to provide specific the calibration curve. So, that can be used and must have full pipe flow. So, I mean all pipe measuring or the flow measuring devices in for pipes should have full pipe flow. So, the next is the pitot tube. So, the pitot tube is nothing but the angular or 90-degree bend which is installed perpendicular to the the point is perpendicular to the flow, whereas the horizontal bend. So, the horizontal part is parallel to the flow. Okay, so, that is the difference. So, it should be a right angle bend. Okay, it is a right angle bend which is installed in a pipe vertically down and also with horizontal leg pointed upstream and parallel to the flow. Okay, and senses both velocity and pressure head. So, if you see this is the pressure head. Okay. So, if you use the Bernoulli's equation, the point here and point here. So, the mostly is a rho by p by rho g and p by rho g plus v square by 2 g. So, the difference is v square by 2 g. So, that h is equal to v square by 2 g. Okay. So, you get velocity and knowing the area of cross section, you can get the. So, q is equal to a into a into v, right. So, you get discharge. Okay, so, the next is the magnetic flow meters. Nowadays, these are really prominent and also these are expensive. So, this is basically works on the principle of Faraday's law. If you remember the Faraday's right hand rule, right. So, there is a magnetic field. So, the magnetic field and the flow is, so magnetic field in the point finger and the middle finger has electromotive force, and the flow which is current which is flowing through the magnetic field, and that can create the voltage, that can not create that can induce the voltage. Okay. So, the induced voltage here will be related to the flow velocity. Okay. So, then so that will give the induced voltage will be related to the flow velocity in this. Okay. So, that is a simple principle. The Faraday's for a given field strength. So, for a given field strength here, see the magnitude of the induced voltage proportional to the velocity. Okay. So, here initially, so the magnetic field being created and then this flow which is basically induces the voltage here. These are the sensors. So, so basically this is the equation, U is induced voltage is estimated by B is the magnetic field strength between the two electrodes, right, and D is the distance between the two electrodes, and V is the velocity of liquid flowing through the metering pipe, and K is the factory set calibrated. Okay. So, each factory is going to have different readings for different devices. Okay. Okay, so the other flow meter which is used to measure the velocity measure the flow rate in pipes is the deflection meter. So, this is the deflection meter. So, deflection meter contains a plate, vane or plate at the center, which is installed at 0.7 or below from the below the center line of the pipe. Okay. If suppose this is 0 to R the distance. So, that means if this is the 2D and this is R, right. So, this is this is the D, the total is D. So, this is the diameter of the pipe D and this is the radius. So, the deflection meter, so the plate which is installed at 0.7 R from the center of the center line, right, and the flow which is going to pressurize the plate or deflect the plate. So, the more flow is going to deflect more compared to less flow. So, the deflection is basically captured in a voltage form. Okay. So, then the deflection versus for the known Q, the amount of deflection is being captured and that is being calibrated, and finally, the deflection meter works for a particular flow rate using the calibration curve. So, so the next is a trajectory meter. So, this same kind of thing we have seen or studied in open channels. So, the trajectory method or projectile method, we have seen some equations there. So, here using the same equation you can still use for pipe flow measurement. So, this is the diameter of the pipe and then this is the horizontal distance and then the vertical distance. So, knowing these two, you can use the equation which is mentioned in the beginning of the lecture and find out the discharge from the pipes. Okay. So, similarly, this is the horizontal pipe, and in case of vertical pipes, so this is a nomograph, you can clearly see. So, knowing the diameter D and then height h. So, height is given on y axis and these lines. So, for different diameter pipes, so these lines are given in the nomograph. So, for example, for a particular I need like 10 inches of height on so 3-inch diameter pipe. So, the correspondingly I am going to get 150 gallon per minute discharge. So, this way you can estimate the discharge from the vertical pipes. Okay. So, so the next is the siphon tube. So, these are very important as far as the irrigation is concerned. Like so, in this, so basically the siphon tubes or the plastic tubes. Okay. So, based on the head diameter and the length of the siphon tubes, the discharge is being estimated. So, accuracy could be plus or minus 10 to 15% and provides in-field method estimation of flow. So, so if you see here, this is the field channel. So, same as here, this is a field channel. From field channel, if you see, this is called a siphon. So, the siphon has been installed into the each furrow, whatever it may be. So, the water level in furrow or the downstream and the water level in the field channel will give the head. Okay. So, here the head of the siphon and then knowing the diameter of the siphon. So, these are the diameters. Okay. So, for 10 for example 10 inches of head and I am for diameter 1 inch, okay, and length 7.5 feet. So, I supposed to get around 9 gallon or 8 gallon per minute. Okay. So, this chart is very important as far as the siphon tubes I mean measuring flow rate through siphon tubes is made. Otherwise, you can also use I mean in field using bucket and stopwatch, you can still calculate the discharge from each siphon. Okay, so and then well, so this is the end of this lecture. So, in this basically we focused on measuring or discharges in open channels and the pipes. So, the basically in open channels, in the last lecture we covered few measuring devices. So, in this lecture, so we covered trajectory method, Deflection flow meter, okay, Parshall flume, right, and then in tubes, in pipes, we have like differential pressure meters. So, like Venturi meter, nozzle meter, orifice meters, okay, and then again the trajectory meter, and then magnetic flow meters, okay, and deflection flow meters. So, and then finally the siphons. Okay. So, so with these two lectures, I mean lecture number 13 and 14. So, we cover most of the measuring devices for both open channel and pipe flows. Thank you.